Swayam Prabha. Digital India. Educated India.
We are back with the fourth module of our MOOCs course, where we are discussing about chain reactions in reactors. Of course, we already had 2 lectures on this, and from there hopefully you have understood the importance of chain reaction. So, just a part of the recap for whatever we have covered in the earlier 2 lectures. You have so far understood that whenever there is a fission reaction, that generally produces neutrons. Now, the number of neutrons produced from each fission may vary between 1 to 7, but commonly it is 2 or 3. But just one fission itself is not sufficient, rather we need to have a chain of such fission reactions. And in this particular context, we can connect this particular module with the previous 2 modules as well. Like in module 2, you have understood while discussing about the artificial radioactivity, you have learned that we can induce radioactive decay to any nucleus by striking it with a suitably charged particle, and the choice for that particle is generally a neutron. But what will be the nature of such kind of neutron nucleus collision? That generally depends upon both the energy level of the neutron as well as the property of the nucleus itself. And from our third module, we have learned that out of several possible kinds of interactions, fission is just one of them, and only very few nucleus like uranium-233 or 235 or plutonium-239, they have some kind of significant fission cross section, so that they can undergo fission reaction when being struck by a thermal neutron. Uranium-238 has a small fast fission cross section when it is subjected to fast neutrons, but generally most of the common nucleus do not have any fission cross section at all. Now, we understand or we identify a particle as a nuclear fuel only when that is having some kind of fission cross section, and just inducing a fission by striking the nucleus with a neutron itself is not sufficient. Rather, the neutrons which are being produced by that fission, at least one of them should induce fission to the neighboring nucleus, then only we can have a chain of reactions. Such kind of chain reaction is quantified in terms of the multiplication factor and reactivity, where this is their relation which we have already learned. A reactor which is having a multiplication factor of 1 and reactivity of 0 is called a critical reactor, where for every fission reaction only one neutron that is produced from the fission is allowed to participate in a subsequent reaction, and accordingly the rate of fission reaction remains constant, so that the reactor is able to produce a constant amount of power over a long period of time. When more than one neutrons are participating in the subsequent fission reaction, we call that a supercritical reactor. Here the multiplication factor is greater than 1 and reactivity is positive, whereas for a subcritical reactor multiplication factor is less than 1. You can somehow relate this process of chain reaction to the cell division that happens in our bodies. Like in a healthy human body, there are always some new cells that are getting produced because of cell division. Similarly, some cells are also dying because of aging issues or maybe some other relevant factors. Now, in a healthy fully grown up body, generally the number of such cells produced because of division is balanced by the number of cells that are dying, and accordingly total number of cells remains more or less the same. That you can relate to a critical reactor. Whereas, a supercritical reactor is can somehow resemble the situation with a tumor or with a cancerous tumor. There the cell division is uncontrolled, so that the number of cells in that particular tissue that keeps on increasing at a rapid rate, and that is not at all being balanced by the death of the cells. Accordingly, total number of cells keeps on increasing. Similarly, a supercritical reactor also will show a sharp increase in the rate of fission reaction, and hence a diverging kind of power production rate, which we generally relate to nuclear weapons. But the most important factor in controlling this multiplication factor, right, like commonly in power reactors we would like to have a multiplication factor of 1, so that we can maintain a critical reactor and hence a constant power generation rate. But in certain situations we may have to increase the power production rate, so we can go for a supercritical situation, or sometimes if we like to shut down the reactor or lower the power generation, we may go to the subcritical stage. But controlling this reactivity is very important, and the most important factor in that control is the role of neutrons. Therefore, in previous lectures we have discussed a lot about different factors associated with neutrons. We have discussed about neutron interaction, which is generally given by a relation like this, and the mean free path characterizes the distance, average distance travelled by a neutron between two successive interactions, or which can be related directly to the corresponding cross sections. And then we went to studying the neutron diffusion theory. And the Fick's law was introduced, which governs the diffusion of neutrons in a particular medium, and using that we can get a balance in the number of neutrons present in a medium, that is the total the change in the number of neutrons present in the medium can be related to the rate of growth and the rate of absorption and also the rate of leakage. Accordingly, we got this one. This is a single energy group or single group neutron diffusion equation. Here this d is the diffusion coefficient, sigma is the absorption cross section, s is a source term, the source of neutron, and v is the velocity of the neutron. So, if we are dealing with a critical reactor, okay, that we can come just after some time. This equation can be modified to a form like this, where we have these two new terms, these which are called buckling. Bg square is called the geometrical buckling, as it is generally a function of the geometry, whereas Bm square is called the material buckling, as it is related to the material properties. And when we are operating with a critical reactor, then the neutron flux, that is this phi, that remains constant to time, hence this term goes to 0, and therefore, for a critical reactor we have this particular condition satisfied, that is Bg square is equal to Bm square. So, this part, up to this part, that is till the previous lecture, we have discussed about, or we have developed this neutron balance equation, and we have discussed about the neutron diffusion theory. So, today we shall be utilizing this equation to study the neutron flux that we may encounter in a particular given kind of reactor in a given geometry, and subsequently we would like to use that in design of different reactors. So, let us take 3 different sample problems, and our objective is to, or 3 different sample geometries I should say, our objective is to identify the distribution of neutron flux for a critical reactor in each of such configurations. And I am actually not sure how much time the subsequent slides are going to take place, because here we are having lots of mathematics to consider. Had it been a normal class where I am dealing with a chalk and board, it could have taken much more than a single lecture, but here as everything I am having on the slides, it may go through very quickly. But still, let us start this. The first geometry we have is that of an infinite planar source. Like our geometry is that of a plane which is acting as a source of neutron, and it is having nearly 0 thickness or extremely small thickness. Look at this diagram. Here by this dark color we have the plate shown. Here we can take this particular coordinate system x in this direction, that is normal to the plane, and these are the other through coordinate systems. Now, here our geometry or our problem definition is the dimension of the plate in the y and z direction is infinitely large. That is, the length scale that we have in the y and z direction are much larger compared to that in the x direction, or we can write, if Lx refers to the length scale in the x direction, is much smaller than length scale in the y direction and a length scale in the z direction. And hence subsequently we can write the gradient in the x direction, gradient for any quantity, that has to be significantly larger compared to the gradient in the y and gradient in the z direction, and hence gradient of any quantity in the y and z direction can be neglected, reducing this to a one dimensional problem, where we can safely consider all variations to be taking place only in the x direction, that is perpendicular to this particular plate. Here we have taken our coordinate system to be at the center line of this plane, and the thickness, as I have already mentioned, the thickness of the sources can be considered to be negligibly small. So, this is the standard form of for the diffusion equation, which we have already studied in the previous lecture and also mentioned in the previous slide. Under steady state, the transient term goes to 0, and so we have the 3 terms, where this is the rate of absorption, where this is the rate of absorption, this is the generation related term, or I should say, I should not say generation, rather this is the neutron diffusion or leakage, where we have used the fixed law of diffusion, and this S is the generation from some external source, or neutrons supplied to the system from some external source. Here we are not at all considering a kind of fission reaction, rather you can think about that this this plate or the planar source of neutron that is immersed into an infinite stretch of diffusing medium, where we do not have any fission reaction happening. Therefore, only thing that the neutron can encounter is diffusion and also absorption by the medium which is surrounding this plate. So, there is no other source of neutron away from the plate, only source is present, that is at the center of this coordinate system, that is at x equal to 0. That means, at this particular condition location we have some kind of neutron source, but we are moving away from the plate, there is no neutron source. Therefore, a small distance away from this neutron source or this plane, we can neglect this term S to, and accordingly this equation simplifies to this. Now, sigma A by D, as per our earlier definition, is the reciprocal of L square, L being the diffusion length. So, this here we are using the Cartesian coordinate system, as that is the most suitable one to this geometry. Accordingly, we have d2 psi dx2 is equal to 1 by L square into phi, which is a very standard second order differential equation, and we know the solution is going to be of this particular form, that is, it is going to be a summation of 2 exponential terms. A1 and A2 are 2 constants whose values we have to identify using the boundary conditions. Now, you see that the neutron flux phi is given as a summation of 2 exponential terms, and both of them are functions of x. Here L is the diffusion length. Here the first exponential term is a decaying one, whereas the second exponential term is a growing one. That is, as we are moving away from the plate, while the first term will start to diminish, the second term will keep on growing. But that is not a very feasible situation to have, because we can always expect, as we are moving away from the plate, corresponding neutron flux that should decrease with x, and that is possible only when the second term is absent in this, and hence this A2 has to be 0. So, we are having this single coefficient A1 that we need to evaluate using the boundary condition. Now, what can be the boundary condition? This is the simple form that we have, but what can be the boundary condition that we need to use? Here, look at the center line or the dotted vertical line, this particular line that is shown in this problem. This refers to the, at x equal to 0 we have the source, and as we are moving away from this, the effect of source gets negated, or rather I should say the effect of source can be eliminated. But at the center line, that is at x equal to 0 location, the source is present, which is continuously emitting neutron following some kind of pattern, and this neutron flux or corresponding neutron current density at this center x equal to 0 should be equal to the strength of the source. Now, let us consider S double prime as the source strength per unit area of the plate. That is, the plate is emitting neutrons at a rate of S double prime neutrons per unit area per meter square, say, for the plate. So, this source strength S double prime or this neutron emission per unit area should be equal to the neutron current density at the center line, that is limit x tends to 0 J x should be equal to S double prime by 2. Why this by 2 is coming into picture? Because you have to consider that S double prime is the strength of the source, but it is equally emitting in both a positive x and negative x direction, and therefore, the positive x direction which we are considering here is receiving only s double prime by 2 or half of that amount. So, the neutron current density at x equal to 0 location should be equal to s double prime by 2, and from Fick's law of diffusion we know that j x is equal to minus d phi dx. So, here we can put this particular form of phi, that is we can differentiate this form of phi and put it back here. So, we are getting this thing, and now putting this limit x tends to 0, we get a 1 to be equal to this particular form s double prime to L by 2 d. Hence, this is the final form of this neutron flux distribution in this infinite stretch of diffuse medium that we are having, that which is surrounding this planar source. Here we are putting x mod of x because this particular distribution is true on either side of this plate, that is for both positive x and negative x this distribution is true. Or you can say that the distribution is on one side of this dotted line is a mirror image of that on the other side. Corresponding distribution is also shown by the dotted line, also shown by, this is the distribution which is already shown here. Now, this is the situation of a very simple geometry of an infinite planar source. Now, you move to our second problem where we basically have a point source one. It is a single point which is emitting neutrons in all possible directions surrounding this, and similar to the previous problem, here this point is also immersed into an infinite stretch of diffusing medium, but there is no fission going on around. This being a point, it can emit in all possible directions of a sphere around this, and particularly when this source is an isotropic one, then its intensity of emission in all possible directions should be equal, and hence instead of Cartesian coordinate we have to take the spherical coordinate while solving this. So, again at a reasonable distance away from the source, the presence of the source can be neglected. So, this is a simple equation, but here while expressing this Laplacian we have to use the cylindrical coordinate system, and the sphere being or the source being isotropic, we can consider this again to be a one dimensional problem, because whatever variation in the flux is taking place, that is only in the r direction, but the other two directions, that is theta and z coordinates, are not having any influence, or rather neutron distribution is symmetric with respect to both of them. Hence, we are having this particular form. Now, this is a slightly complicated equation compared to the previous one. So, we use one substitution where we define a term psi as the product of r and phi. So, if we put it back into this original equation, then we get this particular form d2 psi dr, this should be d2 psi dr 2 minus psi upon L square. So, this equation again is very similar to the one that we have got in the previous slide. It is a homogeneous equation having a very standard solution like this, a1 upon r into exponential minus r by L plus a2 upon r into exponential r by L. Now, what should be the corresponding boundary condition that we must use here? Again, as we are moving away from the source, we are seeing that the flux phi is a summation of two exponential term, one decaying with r and other growing with r, but as we are moving away from the source, the neutron flux should decay, and hence this a2 should go to 0, leaving only this negative exponential term. So, we have to identify only a single coefficient, that is a1 here. How can we identify that? We have to consider that the neutron current density at the center, that is at r equal to 0, multiplied by the area should be equal to the strength of the source. If the source strength is S, it is not S double prime, it is just strength, that is the source, that point source is emitting S number of neutrons per unit time. Then the neutron current density J r multiplied by the area of the sphere of radius r, which is 4 pi r square, should be equal to this S, because whatever may be the value of this r, but what the number of neutrons emitted by the source, that must pass through the entire surface of this particular sphere, which is given by this 4 pi r square, and multiplying that with the current density or neutron current density, we are getting that to be equal to S at r equal to 0. So, we put the Fick's law of diffusion where J becomes d phi dr this particular contribution, and this phi can be replaced with this particular term. So, we get A 1 is equal to S upon 4 pi d, and this is the distribution of flux in the radial direction. So, for both these two problems of an infinite planar source and for a point source, we can just following the standard methodology of solving any differential equation or in a differential equation, we can calculate the final form of flux distribution. It is quite straightforward. It shows that as we r keeps on increasing, as r keeps on increasing, this flux density also keeps on reducing exponentially following this particular trend, that is when r tends to infinity, this should be equal to 0. We have a third problem to deal with, that is of a line source. Here our source, a neutron source, is like a line which is having 0 thickness, but it is having certain length. Maybe you can consider this line strength to be infinite. This being a line, it can emit again neutrons in all possible directions around this, and hence the neutrons coming out of this should pass through a cylindrical surface, just like that shown here. So, following the similar methodology, this is the governing equation, but here we should use the cylindrical coordinate system. So, this is the form, this 1 upon r d dr of r d phi dr minus phi upon L square is equal to 0. And now, we just play around this, that is we break the first differential and then get a form like, and multiply everything with r square to get a form like this. It is a quite complicated form actually, but actually the kind of equations that we are having here, that is known as the Bessel's equation, which has a very standard solution. I hope most of you are aware about Bessel functions or modified Bessel functions. If you are not, you please go to any standard mathematics book and you will find this form for a Bessel function or Bessel equation, which is a form like this, which also has a very standard solution given by Bessel functions or modified Bessel functions, and corresponding solutions will be like this. Here I naught is the modified Bessel function of first kind and k naught is a modified Bessel function of the second kind. Both of them are periodic functions and they have a very standard form, which I do not want to repeat here. But the graphical representations are like this. Here actually I naught and k naught refers to only the 0th mode, they can have several modes, like shown in the graph on the left. Here I naught is having a certain kind of form, which you can check from mathematics books, that it keeps on increasing exponentially with x, whereas k naught keeps on decreasing exponentially with x. Now, we know that x, or you can say r, in this particular coordinate system. Now, as r keeps on increasing, neutron flux intensity or the current density should reduce with time, and hence this I naught should not have any contribution, or rather this A 2 should go to 0, leaving only one term. And now, to evaluate this particular constant A 1, we have to use a condition similar to the previous slide, where assuming a source strength of S, the neutron current in density multiplied by the area of a cylinder should be equal to the source strength. So, at a distance r from the source, or assuming a cylinder of radius r and of height small l, this is the corresponding area of the cylinder is 2 pi r l, or surface area, multiplied by the current density should be equal to S. I am not showing the detailed calculation, you can follow similar procedure, because again J can be related to the gradient of phi following the Fick's law, and this k naught itself is a function of r. So, if you put them, you are going to get that A 1 is equal to S prime by 2 pi d, where this S prime is actually source strength per unit length, S by small l. So, final form of the flux is something like this. Hence, you can see here that we have always started with the diffusion equation for neutrons, but we have dealt with 3 different kinds of problems, 3 different kinds of geometries. Each of them demands a separate kind of coordinate system adoption, but following the standard procedure, we are always able to get a simplified expression for the final flux distribution form. And this exercise also allows us to get a realistic idea or a physical interpretation of the diffusion length. Let us go back to the second problem. where we had a point source. Here this red dot represents that point source, which is emitting neutrons isotropically in all possible directions over a sphere around this. Now, we consider a spherical shell around this. The inner radius of the shell is r and thickness is dr. Then the total number of neutrons that are getting absorbed per unit time within this shell should be equal to the absorption cross section of the shell material into the neutron flux at that particular location into the volume of the shell. Here dV refers to the volume of this infinitesimal shell, and what is dV? That is 4 pi r square into dr. If dr is extremely small compared to r, we can always represent dV with 4 pi r square into dr. What about phi? Phi you have already solved for in the earlier slides. The solution of phi is already available, so you can put this directly here, and we can now simplify this. That is, from these expressions this r and r square cancels out and 4 pi also goes out, leaving us s into r in the numerator, and d upon sigma a is equal to L square. So, we are having this dn, that is change in the number of neutrons, so neutrons getting absorbed, is equal to s upon L square into exponential of minus r by L into r dr. And now, if we want to know the probability of neutron absorption in this shell, the probability is P r dr has to be equal to dn upon s, because s is the total number of neutrons that are getting emitted from the source and dn is the number of neutrons that is getting absorbed in this. So, its probability is the number of neutron absorption per unit for every neutron emitted by the source, that is dn upon s, and putting the expression for dn, it is r upon L square into exponential minus r by L dr. So, now we need to calculate the distance travelled by neutron, the straight line distance travelled by neutron from the source to the point of its absorption. But I do not know why, in fact, I have not found a proper explanation in the books also. That is, common neutron science does not use the distance, rather they use the square of this distance, or I should say the mean square of the distance travelled by the neutron from its birthplace to the place of absorption, and that capital R refers to this straight line distance, and r square is the square of that. So, taking the mean of that square distance, that should be equal to integral 0 to infinity r square P r dr, as r can be of any value from 0 to infinite, and here if you put the expression from this particular expression for P r dr, you are going to get this to be equal to 6 L square. That means, the mean square of the distance travelled by a neutron can directly be related with the diffusion length, or on other words, the diffusion length is a representative of the straight line distance travelled by a neutron, average straight line distance travelled by a neutron from the source to the location where it gets absorbed. And hence, if we have some idea about this diffusion length, we can always calculate this distance travelled by the neutron. But you should not get confused with the earlier defined term mean free path. Mean free path is the total distance travelled by neutron between two successive interactions, but here this r talks about only the straight line distance. Like generally the movement or passage of neutron in the reactor is quite zigzag, it can move from somewhat like this, but this r is actually the straight line distance only from its source to the strength, that is, it will start from this point and finish up at this point and only comprises a straight line between this. So, this distance r is invariably much smaller than the mean free path. But what we can see is that the diffusion length is typically only about 0.4 times of the distance travelled by the neutron from its birthplace to the point of absorption on an average. If we do the same exercise for the infinite planar source, then there you would have got r square bar is equal to 2 L square. I would urge you to try this, for just follow the same procedure on a Cartesian coordinate system, and you should get r bar square is equal to twice of L square. So, by knowing the diffusion length, we can get a proper idea about the distance travelled by the neutron. Now, we enter the situation of multiplying environment. Like the three problems that we have discussed so far, there we have considered the neighboring medium or surrounding medium not to have any kind of fissionable nuclei. But when in a typical nuclear reactor, we may have fissionable nuclei present as well. like the neutron may get diffused through the moderator, but immediately after the moderator or sometimes mixed with the moderator itself we may have fuel nuclei. And whenever there is a fuel nuclei that is being acted upon by the neutron, we can have additional fission reaction, and those fission reactions will produce some further neutrons, or will add some further neutrons into the system. That is what we refer to as the multiplying environment. Corresponding time dependent conservation equation, or time independent I should say conservation equation, that is for a critical reactor, this equation is like this. Here you can see the three terms are the same, like in the previous case we have the absorption term, we have the leakage term related to the fixed law of diffusion, and we have the source term, the external source. But we also have an additional term in between which represents the rate of neutron production because of fission. Here just as per our previous terminology, nu refers to the number of neutrons, average number of neutrons produced for fission, sigma f refers to the fission cross section, and phi is the neutron flux. If the neutron source is absent, then this S goes off, and then we can rewrite this equation to a form like this: minus 1 by phi d2 phi, or the Laplacian of phi should be equal to nu sigma f minus sigma a upon d. Or if you remember our earlier definition, this particular term is referred to as the geometrical buckling Bg square. So, that comes out to be nu into sigma f minus sigma a by d. That is, by knowing the properties of the medium, we can get some idea about this geometrical buckling as well. For a critical reactor, we know that Bg square is equal to Bm square is equal to B square. So, we now have to apply this diffusion equation in multiplying environment to have more realistic neutron distribution in reactors. But before that, we have to remember a few assumptions, like reactor material is assumed to be homogeneous and is having uniform properties in all directions, and the reactor is working under steady state, that is, it is a critical reactor and total number of neutrons remains constant with time as are any other parameters. And third assumption, all neutrons belong to the same energy level. Remember, what we are doing here is the solution of a single energy diffusion equation, that where all neutrons are assumed to have more or less the same energy level, but the variation in the neutron energy level has been neglected. So, we assume all neutrons to belong to the same energy level, that is have identical velocities or identical kinetic energies. So, with that, let us try to study a few reactor designs. The first reactor that we have is for an infinite slab. Here our reactor, you can think this to be an extension of that infinite source problem or infinite plane source that we have discussed shortly back. Here your source is also an infinite slab reactor. Here your reactor is it is an extension of the previous infinite planar source problem. That is, the reactor is of the shape of an infinite slab, or its extent is infinity in the y and z direction, but it is having some kind of finite width in the x direction. So, the total reactor is having a width of a, that is from the central line to the edge, the distance is a by 2 on either side of this, and again the dimensions in the y and z directions to be much significantly larger than the dimension in the x direction, which is a or a by 2. Any variation in the y or z direction can be neglected, and we are having variations to consider only in the x directions. So, this is the equation that we have just derived in the previous slide, d2 phi dx2 plus b square phi is equal to 0, where b is the buckling parameter, which is for a as we are assuming a critical reactor. So, Bg square and Bm square are equal, and that is given by this b square. And again it is very standard homogeneous equation. So, corresponding solution will be a1 cos bx plus a2 sin bx. a1 and a2 are the two constants which we have to evaluate using the boundary conditions. So, what can be the possible boundary conditions? At x equal to 0, what can be the boundary condition? X equal to 0 refers to the central line, and given the geometry, we can easily say that the geometry is a mirror image, or one side of the geometry, one side of the central line is a mirror image of the other side. Accordingly, the central line can be considered to be a plane of symmetry, and hence d phi dx has to be equal to 0. Another way of writing the same boundary condition is phi at plus x should be equal to phi at minus x. Solution point of view, sometimes this is much better to write in this particular fashion. Another boundary condition that we should consider, that is at the edge of the reactor, that is x equal to plus a by 2 or minus a by 2. So, here we take phi equal to 0, because as the neutrons are going out of the reactor. So, we do not expect any neutrons to exist outside the reactor. If we put these two boundary conditions, particularly if we put the first one, that is we differentiate this equation d phi dx and put the limit x equal to 0 and equate that to 0, then we get this a 2 has to be equal to 0, because the differentiator from what we are going to get by differentiation, d phi dx has to be equal to b a 1 sin b x minus of that plus b a 2 cos b x. Now, if you put the limit x equal to 0, of course, sin 0 goes to 0, but as per our definition d phi dx is equal to 0 at x equal to 0, but cos 0 is not 0 and it is possible only if either b or a 2 is equal to 0. B being the buckling parameter, it also is a non-zero number, and hence a 2 has to be 0 to get a proper solution. Now, we apply the boundary condition at the edge of the reactor, and hence putting x equal to a by 2 plus a by 2, we get a 1 cos b into a by 2 is equal to 0. But in order to ensure a non-trivial solution, a 1 can't be equal to 0, and hence cos b by a 2 has to be equal to 0, or in a way b by a 2 has to be equal to 2 n plus 1 to pi by 2, where n is 0 and any other integer, or we can say b n can be equal to 2 n plus 1 into pi upon a, like depending upon the value of n, we can have different values for this b n. So, this actually is leading to an infinite solution, that is we are getting phi is equal to a n cos 2 n plus 1 pi x upon a, where a n refers to the value of this coefficient a corresponding to the nth mode of this function. Practically speaking, all the modes other than when the reactor is critical, after a certain period of time you will not find the existence of the other modes, that is all the other harmonics for corresponding to n equal to 1, 2, 3 etc., all will die down quite quickly, and after some small period of time you will only see the n equal to 0, that is the 0th order eigenfunction or the corresponding fundamental eigenfunction that is existing, and the magnitude of the other eigenfunctions being negligible. And hence, for a critical slab reactor, our solution is like this: phi x is equal to a naught cos b naught x, or that is equal to a naught into cos pi x upon a being the half width of the reactor. But one important condition that we have to consider here we have taken this phi to be equal to 0 at the edge of the reactor, but practically that is not true. Just look at the diagram. Practically we get a profile somewhat like this, that is phi decreases initially from as we are moving away from the center line, phi is decreasing, but while it decreases following more or less the same gradient as per the diffusion theory, it changes quite sharply in the actual case, but remaining constant once we are crossing that neutron level, or once we are coming out of the reactor. But just think about the following the diffusion theory. At x equal to 0 at this particular location, this is not x equal to 0, I should say x equal to a, at this location there is a certain gradient that is being followed by this neutron flux. So, if we just extend that, and we are reaching somewhere here, that is if the neutron flux is allowed to follow the same trend after coming out of the reactor, that would reach 0 at this particular location. This particular distance is often called the extrapolated length, which is d, and corresponding boundary condition is generally called the vacuum boundary condition. So, if for most of the practical reactor problem this extrapolated length is negligible, and hence during calculation it can be neglected and the neutron flux can be assumed to approach 0 at the edge of the reactor itself. But if d is not negligible, then in all the previous calculations, like in the previous slide, this A by 2 has to be replaced by A by 2 plus D. And solution of one group diffusion equation is solution which is beyond this course. For this kind of situation in a weakly absorbing homogeneous media, we can find that D is equal to 0.71 into the transport mean free path, or it is just 0.7104 into 3 times the diffusion length, because we know that the transport mean free path is equal to 1 upon 3 D. These are certain values for common moderating materials, like you can clearly see the diffusion length is generally quite small, starting from 0.142 to in common water to 0.84 and 0.916 in graphite. Correspondingly, the value of this small d or this extrapolated length, that also keeps on increasing. It can be just about 0.3 centimeter in common water, but can be nearly 2 centimeter in graphite. But still, even the largest dimension that we are talking about for diffusion length is only about 2 centimeter. And when you talk about a reactor, common dimensions of the reactors are generally much larger compared to these values, and hence for most of the practical cases this information can be neglected, and the boundary condition can be considered to be phi equal to 0 at the edge of the reactor. But we also have another task like, that is we have to calculate the value of the coefficients that we have discussed. The coefficient A naught can be calculated by using the power produced by the reactor. Practically speaking, if we do not consider, or if you do not impose any other condition, we can't evaluate the value of A naught. Rather, for every different values of A naught, we can have a different solution. So, total power produced by the reactor can be represented by this, where this E refers to the energy released by every fission reaction into the absorption cross section into the neutron flask, and this is being integrated from minus A by 2 plus A by 2, that is from one edge of the reactor to the other edge of the reactor, and corresponding solution is this. So, if we proceed further, we can get A naught to be equal to pi P naught by 2 E sigma F A. Here again I repeat, sigma F is the fission cross section, P dot is the power produced by the reactor, and E is the energy emitted by every fission reaction, which is typically of the order of 200 MeV. So, putting this back in the previous expression, we can get the neutron flux distribution in this infinite slab reactor. But actually infinite slab is very much an idealization, because practical reactors can't have infinite stretch, rather they are having only finite size. So, in the next lecture, or in the last lecture for this 4th module, we shall be discussing about different reactors of finite stretch, where we shall be taking finite sphere as the finite sphere and finite cylinders as the two geometries, and we shall be developing corresponding expressions for neutron flux density intensity, and also we shall be trying to compare different kinds of reactors that are available. Yes. So, for today I would like to close it here itself. Please revise these lectures, and we shall be taking it forward for proper reactor design in the next one. Thank you.